Hey everyone, welcome back to another video for the ICM Python 2.0 curriculum. In this video, we are going to review a few shapes in the reference sheet that are not ellipses, rectangles, lines, or points, some of the more complicated ones. And then we're going to do a little bit of a code along for arcs, which seem to be the thing that trip people up most. But to start out, we are currently in the processing reference sheet, py.processing.org/reference. And we're just going to take a look at a few of the more complicated shapes, starting with triangle and then quad. These are going to come up in the curriculum in a lesson specifically about drawing with other shapes. There is a whole challenge about it that you can take on. We are not going to code these out together, but I do want to talk through them because they work a little differently, and that can be a little to people who are seeing it for the first time. So in the reference sheet, I'm clicking on triangle, and I just want us to take a look at this together. So it draws a triangle. It looks very similar to the rectangle and the circle, except, in a different form. But when we look at the function call itself, it uses the whole word triangle, and then it actually takes in 6 numbers, which is more than we have seen in other functions that we've been using so far. If we read about a triangle, it says that it's created by connecting 3 points. So this is where it gets really different than ellipses and rectangles. With ellipses and rectangles, you are giving 1 point, and it was drawing the shape around that point given a certain width and height. With triangles, because triangles can come in so many variations, that's not really possible to get the variety that we probably want to have. So instead of doing that, they're going to take 3 points. So the first 2 numbers are x and a y for point 1. The second 2 numbers are x and a y for point 2. And then the last 2 numbers are an x and a y for point 3. Then the computer just plays connect the dots with these. This can be really, really hard for students to wrap their heads around since, again, they're not defining a width and a height. And if they want to resize, they need to pick a new point. And this is a great time to remind them that the starter code that we are using, which I will pull up in this tab, has these coordinates showing up in the top up here. I know they're in white. They're kind of hard to see on my screen. They're going to be easier to see on yours. But a really good strategy is for students to put their mouse somewhere on the screen, record those coordinates, go somewhere else, record those coordinates, go somewhere else, record those coordinates, and then code that into their triangle function. If it's not exactly how they want it to be, they can work on moving the points one at a time until it looks better. But that'll help them plan it out a little bit so it's not as much fly in the dark. There's also graph paper that exists for processing for P5, which both use a similar grid pattern. And students could also have copies of that just hanging out by their computer that they can use to plot out some of these shapes. Now, quad is going to work the same way, and disappointingly, it does not have quad as one of my recommended next clicks. Quad is very similar, except it is now making a 4-sided shape based on 4 coordinate points that it's connecting. So it is taking in a total of 8 numbers. Again, the same thing applies. There is no width and height here. It is just taking these points and then it's playing connect the dots with them. Cannot recommend enough encouraging students to plot these out when you are starting to talk about them. Now, the last thing we are going to discuss is begin shape, which is kind of like the next level of both of those. It is under the vertex section of the reference sheet. You can also always do like a Command F and search for words. But begin shape is going to look quite a bit different than the other things we've seen. It's always going to have a function at the top called begin shape and one at the bottom called end shape. And in between those things, it is going to have as many of these vertex functions as you could possibly want. This one has 4. It's drawing a square. That's a little silly when we know we have a rect function, but it's just an example. And it's going to work the same way as triangle and quad, just in a little bit of a different format. It's going to take all of these vertexes and it's going to play connect the dots in the order that you fed it the vertexes. This is a way that you can make some really crazy shapes. You can make shapes that like aren't true polygons. They're closed and crossing over themselves and whatever. But it is an option that is out there in the world. The one thing we need to notice, other than the fact that we are adding, again, as many of these vertex functions between begin and end shape as we could want, is that begin and end shape also have attributes that they can take in. We see in this one that if we say end shape close, it will close it into a polygon with a fill, just like we've seen for ellipse, for rect, for triangle, for quad. If we don't put something like that, it's going to end up looking like this, where it's just kind of blank and empty. Or this, sorry, this is a no-fill one. I don't know if I can find a good example of blank and empty on here, but there are ones where only blank and empty. Or we can denote that begin shape should just be points, or it should just be lines, and that will also look a little bit different. This is one that I encourage you to play with. Please go through the challenge that is in the curriculum, because it's easiest to figure out when you are just practicing plugging some points in. The one that's a little bit more difficult to figure out because it involves a little bit more concept and quite a bit more math is the arc function. The arc function is not only going to take in a lot of values, but it's going to require us to think a little bit more mathematically than maybe we had been doing for the beginning of this course. So there are lots of examples in the reference sheet. I'm going to walk us through this in code. If you would like, please make a copy of that blank canvas with the coordinate text, either by finding it through Google, by heading to our bit.ly/trinket.py, whatever you want, and we're going to code an arc together. So the first thing that we need to know about an arc is that an arc is a piece of a circle. An arc doesn't just exist, it was cut out of a full circle or oval. I like to think about this and compare this to a pie. We had to have a hole that we then sliced a piece out of, or like a serving dish or anything round that you can think about scooping a piece out of. Because of that, the first 4 numbers of our arc, and I'm just realizing now this text should probably always be a little bit bigger. If you are in the same boat as me and you need bigger text, you're going to click these 3 lines, which obviously it's going to not cooperate, and you can make your font size bigger. Should have had that on for all my videos. So an arc, first and foremost, is going to look the same as an ellipse. It's going to have an X and a Y, and that represents the center point of the original circle, the original pie piece that we cut out of. Then it's also going to have a width and a height, which again are talking about that original circle or oval. What did we take this from? The last 2 values are where things get a little nutty for students, because we need to know where are we starting to cut out from that circle and where are we stopping to cut out from that circle. The reason why arcs get so weird for students is because when we think about this programmatically, the default way to program a circle is using radians as opposed to degrees, which many students are used to. Radians base all the angles of a circle out of measurements of pi. A whole circle all the way around is 2 pi. And this corresponds to degree measures, but if you haven't done algebra 2 in a while, or trig or pre-calc or any of those things that are a little bit more reliant on the unit circle, this might be a hot mess. This might be really, really hard, and it could be really, really hard to get those measures of pi written into your code in a way the computer understands. So what I like to recommend to people is just turn all of your starts and stops into degrees using a function called radians. And what radians does is it takes in a degree measure and returns radian value. Oops, let's make this a little bit bigger. So let's take a look at what that's going to be for us. So I'm going to start out by making an arc, and I'm going to start just like the first ever ellipse I made. It's going to be in the exact center of my screen. And I'm going to make this pretty large. So I think I'm going to make the width and height both 300. So it's a perfect circle. Now, when we think about the start and stop, both of these are going to use the radians function to turn one of my degree measures into a radian value. So I want to think about making a half circle. And I know that half circles are 180 degrees. If I think about my circle cut into 90-degree chunks, it's 0, 90, 180, 270, and back to 360. So I'm going to try saying, let's start at 0 and let's end at 180, because I know that's roughly half a circle. So I'm going to hit stop and then run. And we can see that we now have half a circle appearing on our screen. You'll notice that this is like the smiley face half a circle. If I wanted to invert it, if I wanted it to be the other way, I could just swap my numbers of starting and stopping so that it starts at 180 and stops at 0. And now when I hit play, oops, is that not going to work for me? I have an error somewhere. Hold on while I figure that out. Oh, maybe it needs to go from 180 from, I think it doesn't like starting big. It might need to go 360 to 180 or 180 to 360. Let's see what it does from 180 to 360. There we go. Going from 180 to 360, we'll flip it around the other way. Technically, 0 and 360 are the exact same point. Apparently in processing.py, it sees it a little bit differently, but changing that last value to 360, now it's going to go all the way around. We can also think about getting a half circle on the left or the right by doing, for example, 90 to 270, which now gives us half a circle. Or we can think on the other side about doing 272. We'd have to figure this out in our head, do a little mental math that I'm not ready for, but something beyond 270. And I believe we should be able to go over 360. It should fix that up for us, but we aren't constrained to half circles. We could plug in 45 to 97 and get a little tiny arc. We could plug in 97 to 103 and get an even smaller arc as we work our way around the circle. These are all available to us. I'm going to make this just a little bit bigger. And I'm going to change these values. If I start to make my values of my original circle smaller, we'll see that my arc gets smaller. So instead of 300, let's make these both 200. The size of my wedge, like the angle measure, the same. The size of the original circle, smaller. So it looks a little bit smaller. Again, this can be incredibly overwhelming for everyone when they are trying arcs. I encourage you to just mess with these numbers. If it doesn't show up, problem solve, try different values, see what happens when you stick other things in. This can be a really useful one to have a diagram open of degree measures around a circle, or there are some unit circles that have units and degrees. And this can help you figure out how to successfully draw arcs. One thing I do want to point out is with our arcs, there is an optional final 7th value that we see demonstrated in the reference sheet. Open leaves a blank end that is just white with no line. Chord closes it. And pi is what's going to make it kind of like a Pac-Man. And just note that it's pi, P-I-E, as opposed to the P-I, which is being used for radian measurements. Arcs can be tricky. Please play and explore. If you choose to never use an arc or to only use arcs sparingly, that is absolutely your prerogative, but it is a useful tool to have in your back pocket. Good luck using arcs, and I'll see you in the next video.